Welcome to the Sizer online tutorial. In this video, we will go through the features and different equations on the lateral support options available in the software. So we will start off this video by discussing some design settings, and we will focus on built-up beams and lateral stability. If you click the settings in the menu screen of the page, then navigate to the design tab, you will see there is a section devoted to lateral stability factor KL. For both sawn lumber and SCL, referenced in clause 15, CSA permits KL may be assumed to be 1 if certain lateral support and height to width ratios are met. It can also be calculated using the equations in the glulam clause, which is clause 7. Glulam oriented in the normal direction must be designed with the more rigorous equations, but SCL members, like built-up lumber, may use either method. Sizer gives users the flexibility for determining how the lateral stability factor KL is calculated. For the first option, which we can call the prescriptive option, you are permitted to assume KL is equal to 1 based on the depth to width ratio or aspect ratio. For example, a relatively stocky section with a 4:1 aspect ratio is permitted even if no intermediate support exists, but can go up to 9:1 if both the tension and compression edges are held in place. After applying the load and running the design of this beam with a 6.5:1 aspect ratio, you can see that the KL is equal to 1. But notice that KL is not equal to 1 if I remove the compression edge support, a feature which I will explain in a few minutes. In other words, if you have the prescriptive option selected, Sizer first checks the requirements of clause 6.5.4.2 for solid sawn lumber or SCLs, but if the member does not meet the aspect ratio requirements, the software will follow the more rigorous calculations for lateral stability from clause 7.5.6.4.4, which, as you can see from the equation, is a lot more tedious if you were to do this by hand. As for the calculation method, it is related for built-up members on how well their individual plies are fastened together. By default, Sizer will assume that connections of each ply of the built-up beam is not adequate and performs the calculation based on a single ply. You will notice a big difference in the bending capacity depending on the option selected. In fact, let me show you. Here is a 3 meter long 3-ply nominal 2x10 built-up beam consisting of number 1, number 2 SPF. If you were to calculate KL based on a single ply, the resulting KL would be 0.508, resulting in a moment resistance of 6.84 kN per meters. Now, if we selected the full member width, KL would be equal to 1.0 and the moment resistance would be 13.48 kN per meters. Information related to the lateral stability calculations will automatically be reported for you in the design results. 6.5.4.2.2 provides a prescriptive method to fasten the plies together in order to assume all members act as a unit for the calculation of lateral torsional buckling, that is nailed spaced at 4 times the depth of the beam. There is some question as to whether this is really sufficient, and research is ongoing on this topic. As an aside, the prescriptive National Building Code Part 9 requirements says 38 mm members are laid on edge to form a built-up beam. Individual members shall be nailed together with a double row of nails not less than 89 mm in length, spaced not more than 450 mm apart in each row. Back to CSA 6.5.4.2.2 means, for example, that for fastening a 12-inch deep built-up beam, fasteners may be spaced at up to 4 feet and still assumes that all the plies act as one beam. If you are unsure about the adequacy of the connections, we suggest that you are conservative and select the single ply width settings. So, we have talked about the prescriptive option where the software is permitted to assume KL is equal to 1, and we have briefly talked about the calculation method. We also need to talk about the unsupported length LU option used in the calculation of the KL factor. By default, unsupported length LU ends at points of zero moment is not selected. When not selected, This means that LU is calculated based on points of lateral support, typically taken as the length between points of bearing where lateral support is required. The software does give you the option of calculating LU based on points of zero moment instead, which is the method used for steel beams in the Canadian Steel Standard CSA O86. But this means that the LU is typically shorter, and therefore less conservative than if LU is calculated based on the distance between lateral supports. This is why we suggest not selecting this. Just to be clear, LU is used to calculate the effective length LE in the case where no additional intermediate support is provided, which is then used to calculate the slenderness ratio CB. This affects the resulting lateral stability factor KL for a beam. Let's look at an example to see how this last feature works. Looking at a slender of 2-span continuous beam that has 2.4 meter segments, with uniformly distributed dead and live load, and lateral support only provided at points of bearing. Because the beam is continuous over 2 spans, this creates a negative bending zone around the center support. In this case, if the unsupported length LU feature is not toggled, for both positive and negative bending, the length LU will be taken as 2.4 meters, or the distance between supports. Now, looking at the same example, but if we toggle the option to use the unsupported length LU feature, you will notice a difference in the LU for positive and negative bending. In the case of the positive bending, the member length LU is taken as the distance between the end support and the point of zero moment along the length of the first span, so about 2.03 meters in this case. Then, for negative bending, the length LU is taken as the length between zero moments for the negative side of the member, so in this case it would be 0.6 meters. Remember when I mentioned the compressive edge and tension edge supports earlier in this video? Here is how you go about modifying the support conditions. When designing a bending member in beam mode, depending on the material type you specify, the lateral supporting conditions are going to change automatically. If you specify the material type as a beam, the default setting of the program is to assume lateral support at the top and bottom of the beam at points of support. If you specify a floor joist or roof joist, since sheeting is fastened to the top of the members creating a system and providing lateral support, the default lateral support spacing is to provide continuous lateral support along the top and support at the bottom at only the supports. You can always specify exact lateral support spacing details. For instance, if there is a beam supporting a floor joist system spaced at 400 mm on center, you may want to specify an exact support spacing on the top of the beam, as it will affect the calculations for KL. When designing a beam with multiple spans, the option to toggle laterally supported at support becomes available. This feature is for interior supports and gives you the choice for designing certain supports with a lateral support or not. This will have an effect on the lateral stability factor, since depending on whether or not the option is checked, the span used to determine the unsupported length LU, the effective length LE, and therefore the slenderness ratio CB will not be the same. That being said, ultimately, the moment resistance of the beam will vary depending on this feature. Using our original built-up beam with an additional 3 meter span, we will run the design with a 1.5 kN per meter dead load and a 2 kN per meter live load applied to the beam. You can notice the difference in the resisting moment. In fact, in this case, the beam can resist twice the moment force when laterally supported. Otherwise, it generates a failure. By looking at the additional data, we can pinpoint the nature of this difference. As mentioned earlier, the feature has affected the lateral stability factor KL. Furthermore, by looking at the calculations for the lateral stability, we can see that the unsupported length is twice as long when it's not laterally supported. This also generates an effective length that is twice as long, as well as a higher slenderness ratio CB, which is used to determine the lateral stability factor KL.